And then the last one we spoke about is the fixed position layout, which is used normally for projects and for very huge, bulky, or heavy kind of production. For instance, you're building a ship, you're building aircrafts or houses. Production is done at just one place. That's why the name speaks for itself, fixed position layouts. The output, what we intend producing, is so huge that it cannot be the typical type that you can be moving around. I can imagine building a house and you can produce the wall of the house at some point before you bring it to the site. It never happens. So where the house is supposed to be built, that is where we are supposed to site the production. And so that's the name speaks for itself as a fixed position layout. Now, some characteristics here is that equipment usually are leased or subcontracted, of course. So it's just like a one-time kind of production exercise. You need highly skilled workforce to perform specialist jobs. You don't just take any general purpose person or just anyone to build an airplane. You need highly skilled engineers, computer guys, programmers, very skilled people. And then high wages for workforce. Once the person is, once you're using skilled labor, definitely you should be considering high wages for such kind of people. And there's also a low fixed cost, because the equipment may not necessarily be owned by whoever is doing the production. You can lease, you can hire. Once you're done, you take whatever equipment back to whoever owns them. So if you're a producer, in that case, you don't necessarily need to acquire all the kind of equipment you need. Okay, so let's look at designing the process layouts. Now, how do we design a process layout scientifically, so that there will be some backdrop of science behind the layout? Now, I wanted to take maybe a second and ask yourself, observe a typical designer. We'll call them seamstresses or tailors, or probably just any organization, small-scale business, and ask yourself, what informed their layout? Why do they have the machine here? Why do they have the knitting machine here, or the sewing machine here? And why do they cut here? Why do they iron here? For some reason. So you understand what informs that kind of arrangement. Now, I said there are two techniques used to design the process layouts. We have the block diagramming, and we also have the relationship diagramming. So we'll go through them briefly and just have a fair idea. Under the block diagramming technique, what we do is we gather historical or predicted movement of material movement between departments. So what is the flow of interaction between each department? Now, if I would prefer to use the basic environment like that of a seamstress, because I'm sure probably that would be something that we all would have some observed at some point. Now, how often does the seamstress move from the table she does the cutting to where she irons? How often does she move from where she irons to the sewing machine, or probably from where she irons to the knitting machine? That's what we refer to as the historical data. If we can collect data or kind of have an idea of the interaction or the relationship between each unit or each workstation, it gives us what we call a load summary, or a summary of the interactions, and we'll call that our load summary chart. That will give us a fair idea, so that if you are citing these two workstations, if you notice that, well, the seamstress moves a lot or interacts a lot between ironing and then the cutting table, the ironing table and then the cutting table, then you should be considering putting these two close enough to each other. That is some science behind what the block diagramming technique is talking about. And it says that calculate the back and forth movement, or what we call the composite movement, between each pair of departments and rank them from the most to the least. So exactly, so like I'm saying, as you take data or information on the interactions between each workstation or each point or each functional area, I'm sure they are integers, so you can easily count them. And so you look at the total counts and then arrange them in order, so that you prioritize them, how you arrange them. And so assign each department to a block on the grid, so that the non-adjacent or distant further than a block are minimized. Okay, so we'll explain this one. When we talk of, we'll use some diagrams to explain this, but when we say one department or one workstation is non-adjacent to another, it means that you may have to move more than 2 blocks to get to the other department. But when one is adjacent, it means it's just directly opposite or just just buy it or something. So now add information. So we'll take stuff or the equipment vendors, the safety regulations, operating manuals about the space required of the department. So these are some other things that you also need to. Now, for instance, if you're putting the ironing something against something that could probably have some volatile feature, could result in some fire, you may want to consider that. That's a safety regulation. So aside collecting the data and all that, there are other things that you also need to consider. Okay, so this is a basic example. So I have a table here that has, let's say this is a university. A university is relocating to a new campus and wants to revise the current facility layout. So it's shown as this. So for instance, maybe they think their current layout is not so efficient, so they want to. Now, so the health center, so these are kind of new departments that the new campus will have. There will be a health center, there will be a library, there will be a lecture, there will be lecture halls, there will be food area, and there will be the administration, and then the halls of residence. So 1, the health center, 2, the library, in that order. So you do see that from the table, between the health center and the library, there is no interaction. But between the health center and then the lecture halls, there are 125. And between the health center and then the food area, there is 40. And so this is from, to and from, to and from. If I want to look at the health, from the food area to the health center, that would also have a certain difference. That would be 60. So you can just look at this matrix and just try and understand how it works out. See, when we talk of the back and forth movement, it is possible that someone can move from the health center to the lecture halls, and then someone can also move from the lecture halls to the health center. So it's a back and forth movement. You must look at both instances. Okay. So for instance, from the health center to the lecture halls, that is from 1 to 4. Sorry, 1 to 3. That's 125. But if I want to look at the lecture halls to the health center, that is, you hardly have anyone moving from the lecture halls to the health center. Okay. All right. So this is the current layout of the institution. So you do see 1, 2, 3, 4, 5, 6. So kind of that's how the campus looks like. So that's more like a sketch of where the departments are located. Now, let's understand what we call an adjacent movement and then an unadjacent movement. 1 is adjacent to 3. And again, 1 is adjacent to 4. 1 is adjacent to 2. Now, diagonally, we can also say 1 is adjacent to 6 and it's also adjacent to 5. But if you consider 3 and 4, you would have to move from 3 to 1 and then from 1 to 4 before you can have a relationship between 3 and 4. So between 3 and 4, we will say that it's a non-adjacent movement or layout, because you would have to move 2 blocks to kind of move from 3 to 4. Again, if you want to move from 3 to 5, it's the same. It's non-adjacent. You would have to take some extra distance. But if I have to move from 3 to 6, it is just 1 step. So that's the difference between what we call an adjacent movement and then a non-adjacent movement. So from the table, we did the composite movements. So between 1 and 2, it's 0, and then 1 to 3, it is 1 to 5. Now, if you look at the arrows are facing both forward and back. So it's a sum of moving from 1 to 2 and then 2 to 1. That's what that arrow means. So if you have an arrow, a line that has arrows at both ends, it means that it's a back and forth movement. And that's so we kind of do this. And when we are done, we just listed all the movements upwards. Now, the second arrangement down is what we call the arrangement, where we try to do it in more like a descending order from the highest to the lowest. And so we have 3 to 5, which has the highest composite movements, and then it's 2, 3, 5, then 3 to 6, 240, 5 to 6, 160. It follows in that order. And the least is between 1 and 2, 1 and 5, 1 and 6, 2 and 5. They all have 0, 0, 0, 0. Okay, so given this information, we are going to represent this same data we have been able to accumulate here on the graph. So you can see that between 3 and 4, we have a total movement of 40. Between 3 and 1, it is 125. Between 1 and 4, it is 100. Between 2 and 4, it is 105. And in that order, you also see between 6 and 4, it is 80. And then 3 and 5, it is also 160. Now, you see, if you have this represented on a graph like this, you can see that there are some departments that interact with other departments, and there's quite a chunk of movement, but they are quite far away from each other. Now, it means that it will take extra time, extra effort, extra resources to move between these departments. And so what this technique is supposed to do is to help us rearrange our layout, or reorient this layout so that the non-adjacent loads are reduced. Now, for now, our total non-adjacent load is 505, which means that if it's a sum of what happens between 3 and 4 plus what happens between 6 and 4, and what also happens between 3 and 5, and then 6 and 5 as well. So when we sum all these, we have a total of 505. So when we rearrange this, we put all those interactions together. Those departments that do not have any interactions with each other, we can separate them. They can become the non-adjacent ones. And those that have some interactions should be the ones that should be closer to each other. So let's just go one step back and look at the previous diagram. Now, you see, what we've done is, for instance, if you take 1 and 2, 1 and 2 do not have any interaction. So 1 should not be close to 2. There's nothing. We can keep 2 as far away as possible from 1. But if you consider, say, 1 and let's say 3 and 5, there's some interaction of 235, and they are so far away from each other. So what you have to do is do this rearrangement to ensure that 3 and 5 are kind of close to each other. So that's all we did. And now if you see this, you see that 3 and 5 are that close to each other. It's just one block, and that it becomes adjacent. And after doing this, you see that all our non-adjacent loads are 0. So we have a total non-adjacent load of what? 0. Once you do this, you have improved on your facility or your layout, and that will help reduce time, increase your efficiency, and a lot, and it saves the company a lot. It makes it even more competitive. Okay, so I hope this lesson was insightful, and the conversation will continue from here. So thank you for this. I'll see you in the other session.